Hello everyone. Today I am going to discuss about the course, namely conductive heat transfer. And before I'll provide the detailed content of the subject, that is heat transfer, I'll provide the relevance of the subject, importance of the subject, and its application of the subject. So the word heat, you might be aware about the word heat in thermodynamics. So normally in thermodynamics, the heat, which is the form of energy in flowing condition. So the heat which is in transient. So the heat which is transferred from high temperature to low temperature, that because of temperature difference, that is known as comes under the category of thermodynamics. So normally in thermodynamics, in classical thermodynamics, the heat is quantified by two distinct status. One is energy in storage, and the another one is energy in transient. So as you can see in this picture, the thermodynamics deal with the quantitative energy of states when the system undergoes a process from one equilibrium state to another equilibrium state. So as you can see in this picture, the cup of tea having temperature is 70 degree Celsius and the ambient temperature is 20 degrees Celsius. So of course the heat will transfer from high temperature to low temperature. So by this way, the temperature of the tea can be reduced. Okay. So in thermodynamics, it tells us about the content of heat, the quantity of heat at the initial stage and the final stage. But in thermodynamics, it fails about the information which is provided at which rate the heat is going to be transferred, right? So that's why in heat transfer is deal with the rate at which heat is going to be transferred. So in this subject of heat transfer, we have to discuss about what is the rate of heat transfer, and it is very important as far as the design of any equipment or any design any heat transfer process. So and also how long the system will transfer the heat. So this type of information we can also obtain from the heat transfer. So and also the mass transfer, but I am not going into that detail because I am exclusively discuss about the heat transfer. So the basic mode of heat transfer is conductive heat transfer, and in the conductive heat transfer, normally it is because of vibration of the molecules in the lattice structure. Okay, as you can see in this picture, this is the first molecules which gets excited, which gets receive the energy or the heat from any sources, and it start to transfer its heat or its energy to the neighboring molecule, right? So by this way you can the heat can be transferred from one molecule to another molecule in the lattice structure. So, and another mode of heat transfer is convective heat transfer, but the convective heat transfer is not a basic mode of heat transfer. As I said, the basic mode of heat transfer is only the conduction. In convective heat transfer, the fluid is flowing from and because of the fluid is flowing, the basic mode of heat transfer is getting disturbed. Okay, so that is why in this way the heat can be transferred from surface to the flowing medium, and that's why it is known as convective heat transfer. And another mode of heat transfer is radiative heat transfer, but for this lecture, I will just restrict myself to the conductive and convective heat transfer, right? So, conductive heat transfer is normally in a solid and fluid, or also in gas. So, and in solid, the lattice vibration is the main responsible factor to transfer the heat, whereas in liquid in fluid or in gases, the random motion of molecules are the main cause for the heat transfer, right? And in convective heat transfer, of course, as I said, it is not a basic mode of heat transfer. Basic mode of heat transfer is conduction, but because of the heat transfer get disturbed or get affected because of the flowing of fluid. So that's why it is known as convective heat transfer, right? Okay. So as I said before going to the detailed content of this course, I need to discuss about the importance and its application. So the main importance, the heat transfer prevails everywhere, like in nature as well, like what we do in our daily life. So we take food to take the and by taking the food we get some energy. So after the metabolism, the bloods are allowed to flow in the arteries, okay, and by at the same time we are able to do work, and by doing work we have our skin or human skin is maintained at certain temperature, so or maintained at very high temperature. So the heat is going to be transferred from our body to the ambience, but the ambience has to be conducive enough to transfer our energy from our body to the ambience, okay. So that's so in this way the heat can transfer from our body to the ambience. So this is one example, and it is also the same way the heat can transfer in plants, heat can also transfer in animals as well. So this is the one examples of heat transfer. So now coming to the application part of heat transfer, as you can see in let's consider you have let's consider a power production unit. So normally in the production of energy or in the generation of energy, we used to burn the fossil fuel. So 70% of the heat is generated from the burning of fossil fuels. So during the burning of fossil fuels, it is burned in the furnace. So the design of furnace, so after the completion of the burning process or the combustion process, the heat must be supplied to the next system or the further process, okay. So to sustain that temperature or to maintain the temperature within the furnace, the heat must be exchanged with the equipment or with the ambience. So how we can design or how fast the heat can be transferred from furnace to the ambience or furnace to the further process, that comes under the category of heat transfer. Like suppose if we have a exothermic reaction in which the downstream is maintained at very high temperature, okay. So to exchange that heat from the high heat flowing from the high heat content to the another fluid, so it must be contact with the fluid or with the cold coolant to exchange the heat, and that is performed in the heat exchanger. The same type of process can be taken in the boiler as well. So this is very important as far as technological development of the subject, and as far as the process economic of the plant, okay. So this is all about the application of heat transfer. So in summarize, I can say of course the word heat, which is closely related with the thermodynamics, but it does not provide the information about how long the process will take place. Means whenever the system goes under the equilibrium process, or when the two systems are in contact with each other, and during the thermal equilibrium process, how long the process will take place or how fast the process takes place, at this point the thermodynamics fails. So that is why the science which provide the information about how fast the heat is going to be transferred or at which rate the heat is transferred, we can study in this subject, heat transfer, okay. So as I said, of course the heat is transferred because of the temperature difference. So let's consider the temperature is maintained at the different temperature maintained at a surface, okay. So this is the temperature axis and this is the distance. So as we move in the plus x direction, the temperature will decrease, okay. So let us consider this is the temperature axis, at which different temperature is maintained, and this is the distance from and this is the origin point. Okay. So as we move in the plus x direction, the temperature is going to be continuously drop. So we have the negative temperature gradient. So, and this is the direction of heat transfer. So the most important information we have to, so let's consider this is the heat, overall heat flow in this direction. So we can say the heat is a scalar quantity which provide the information about the direction in which heat is going to be transferred and the magnitude of what is the magnitude of that heat transfer. Okay, so we can say the temperature is a function of x. So as we move in the x direction, the temperature is going to be decreased. Temperature is a function of x. So let us consider area normal to the direction of heat flow, that is ax. So this is the control volume, or I can say the area in which we have to evaluate the amount of heat which is going to be transferred, right? So this is the cross-sectional area in across which the heat is going to be transferred. So in order to, and why I'm considering this area, so basically this is the perpendicular area or the cross-sectional area which across which the heat is going to be transferred. So the area which you are going to be considered, that must be perpendicular to the direction of heat flow. So in this way you can identify the amount of heat flux, right? So this small qx, where q is the heat flux and x is the direction in which heat is going to be transferred. So q is equal to the total heat flow per unit area. So area of your control volume. So if the area is going to be 0, like that means if the value of area is going to be 0, that will provide the information about the total amount of heat flow. So at 0 value, the total heat flux you can obtain. So basically this type of information, so this information is very important as far as the mathematical equation or the derivation of mathematical equation for heat transfer. So this is the basic foundation equation of which is provided by the very famous mathematician from France, that is Joseph Fourier. So Qx, this is the heat flux, is equal to the minus k dt upon dx. So where where k is the thermal conductivity and the dt upon dx is the negative temperature gradient. So as you can see, this is the negative temperature, the minus sign which is present in this mathematical equation, so which is deliberately provided because the negative temperature gradient is comes into the picture. So to obtain the positive value of heat flux, the minus sign has to be kept because the negative temperature gradient will compensate the minus sign, and in this way you can have the value of positive heat flux. Okay, so this equation is the foundation of overall heat transfer. So where the K is the thermal conductivity of the property, or I can say the transport property of the material. Okay, so like transport property, like which transfer the heat or transfer the property which you transfer the quantity which you want to be evaluated. Like in case of mass transfer, the diffusivity is the transport property. Like in case of momentum transfer, the viscosity is the transport property. Similarly, the transport property, the thermal conductivity is the transport property. Or I can also explain, like suppose if you have a metal plate which is maintained at room temperature, and suddenly if you put a piece of ice on that metal piece, on that metal bar, so actually we are trying to create a disturbance within the metal surface. So how fast the temperature disturbance will propagate in that metal piece, that will convey by that messenger, and that messenger is known as thermal conductivity, right? So yeah, exactly. So this is the basic foundation mathematical equation for all conductive heat transfer. Now I am going to discuss about the derivation of heat diffusion equation. So before going to the derive the definition of heat diffusion equation, we have to just discuss about the mathematical form of this Fourier's law of heat conduction. So basically the rate of heat conduction through a wall, or I can say the control volume, which is proportional to the temperature difference across the wall, and the cross sectional area through which the heat is going to be transferred, and it is also inversely proportional to the thickness of the wall. So the rate of heat conduction is directly proportional to the area and thickness, temperature difference, and the thickness of the wall. So like this. So Q conduction is equal to minus Ka T1 minus T2. T1 is the wall temperature at one surface, and T2 is the wall temperature at another surface. And this is the heat. This is the direction of heat which is flowing in x direction. So ultimately the Q conduction is equal to minus Ka dt upon dx, where K is the thermal conductivity or the efficacy of massive propagation in the medium. Okay, so as I said, the negative sign because the temperature becomes less as the x distance is increasing. So in the limiting case, or I can say at delta x tends to be 0. So this equation is reduced, or the reduced form of this equation is Q conduction is equal to minus Ka dt upon dx, and the unit for SI unit for the rate of heat transfer, that is watt, and this is known as Fourier law of heat conduction, which is provided by the Joseph Fourier. So as I said, this K is the thermal conductivity, and thermal conductivity basically is the transport property which relates with the potential of that quantity, which causes the heat flux, which causes the flux of that quantity. Okay, so normally in the solid system, or in the metal, or I can say the things in which the atoms are closely packed, for that kind of arrangement, the thermal conductivity is more as compared to the fluids like water or the organic solvents or any oil or something like this. So you can see the thermal conductivity is vary as per the different for isotropic system is thermal conductivity may vary with x direction, with y direction, with z direction, but it may not be vary. So for isotropic system, the thermal conductivity will be constant for all directions. So as I said, this temperature difference is the main cause for heat transfer, and this is the conductive heat transfer equation. So where Q double prime or Qx double prime is the heat flux, which is equal to the total amount of heat flow in x direction per unit area, is equal to the minus K delta T upon delta x. So this is the heat flux, which is actually the vector quantity. So now we have to discuss about the heat diffusion equation, but before deriving that heat diffusion equation, or before approaching that heat diffusion equation, we have to discuss about the control volume and control surface. So basically the control volume is the imaginary area, or the area of interest in which we are evaluating the amount of heat which is flowing across that particular space. Okay, so that is known as control volume, which is surrounded by the imaginary boundary, and the imaginary boundary which is known as control surface. Okay, so let's try to apply the so this is the control volume, and this is the control surface. So CS represent the control surface, and the CV represent the control volume, and the heat which is flowing across the control volume. Okay, so if we apply the first law of thermodynamics, that is the law of conservation of energy. So that is let's consider this is the amount of energy which enters into the control volume, and this is the energy generation, and this is the energy depletion, or and this is the energy, this is the amount of energy which is coming out from the control volume. So we have to, and this is the amount of energy which is stored in the control inside in the control volume. So if I want to convert this information in the mathematical form, so we have the we have to apply the law of conservation of energy for control volume and for control surface as well. But for considering the system is in steady state, so this is the energy conservation equation, that is energy in minus energy out plus energy generation or energy depletion, and which is and the algebraic summation of all three terminology is equal to the change of energy within the control volume. Okay, so this is the rate of change of energy within the control volume. So for control surface, it's a as I said, it's a hypothetical or it's a imaginary surface which does not have their own mass, and because they don't have their own mass, control surface, so that's why it cannot store the energy. So okay, so that's why it is if we apply the energy conservation principle for that one, so you have energy in and energy out, and because as I said it does not have any own mass, so it cannot store anything. So if it is not stored, so means the rate of change of energy within the at the control surface, that term will disappear. So for steady state, we have to discuss about what will be the final form of this equation for a steady state. So because energy cannot be generated, okay, and the energy cannot be stored, so only the term left with us for control volume, that is energy in and energy out. Similarly for control surface we have the same equation. So this is the application of law of conservation of energy for control volume and control surface, at which temperature difference will takes place, and the vertical axis will represent the temperature variation. Okay, and the heat is transferred within the solid body. So of course the heat which is going to be transferred within the solid body, that is known as conductive heat transfer, and from the control surface to the ambient, the mode of heat transfer is convective heat transfer. So this is the solid object which is exposed at the ambience or in the flowing air condition, and at one surface the temperature is maintained at temperature is T1, and at the another surface temperature is T2. So within the control volume or within the solid object, the temperature vary from T1 to T2. So of course T1 is greater than T2, and from T2 to the temperature of the ambient, that is T infinity, it has to be also changed. So our objective is to identify what is the form of law of conservation of energy exactly at surface balance. So from control volume or from solid object, the mode of heat transfer is conductive heat transfer, and from surface of the control surface, from the control volume to the ambient, the mode of heat transfer is either convective heat transfer or the radiative heat transfer. But in the absence of radiative heat transfer, we can say exactly at the surface, the energy which is coming out from the solid body to the ambient, the same amount of energy can be emitted or can be transferred from the solid body to the ambient. So that's why this conductive heat transfer is equal to convective heat transfer. But only the difference is the temperature profile will be changed. Okay, so as you can see in the solid object or in the solid body, the temperature profile is linearly vary, whereas from from surface to the ambient, you can observe that the sharp temperature steep difference from T2 to the ambience. So unless and until the temperature is not achieved T infinity, so exactly for that particular time of period, the temperature change will take place. Okay, so in this we can say the temperature is a function of time, and in this case the thermal conductivity of solid is very high as compared to the air. As I said just before in the last slide, in the solid objects, the arrangement of molecules are very closely packed in the lattice structure, whereas in the air, the molecules are randomly move or random motion, and because of the random motion they can collide, and that after the collision the energy will the kinetic energy will increase. So that's why the thermal conductivity is vary in fluid and in solid as well. Yeah, so this is the thermal boundary where the temperature where the exactly at the boundary the mode of heat transfer, conductive heat transfer is equal to the convective heat transfer, right? So we have to derive the heat diffusion equation. So let us consider the simplest possible geometry, because for the derivation of that mathematical equation, that very famous equation, that is Fourier law of heat conduction, we consider only one direction, but in practice the heat can be transferred in all possible directions. Okay, so the heat can be flow in x direction, the heat can be flow in y direction, and in fact in z direction as well. So we have to consider a simplest possible geometry or Cartesian coordinate. We have the cube. Okay, so in this cube, and across this cube we have to apply the law of conservation of energy, or we have to quantify the amount of heat which is getting transferred across this control volume. Okay, so let's consider this is the cube, and having the dimension is dx, dy and dz, and the amount of heat which is transferred in x direction, or the amount of heat which is entered through x phase, that is qx, and the amount of heat which leaves from the x plus delta x phase, that is qx plus dx. Okay, and this is the amount of heat which is entering through y phase, that is qy, and this is the amount of heat which is coming out from the y plus delta y phase, that is qy plus dy. Similarly for z phase, okay, the amount of heat which is enter from the z phase, that is into the z phase, that is qz, and the amount of heat which leaves from the z plus delta z phase, that is qz plus dz. Okay, and we have to also consider this Eg means the rate of energy generation. Okay, so energy generation is the energy is generated within the control volume, and the energy which is stored within the control volume. So because of the flow of energy from one phase to another phase, or so whatever be the energy change takes place, that must be stored within the control volume, right? Okay, so we have to identify the amount of what is the amount of energy which enters into the control volume, and what is the amount of energy which leaves from the control volume. Okay, so these are the different phases. So this left side left one is the x phase. Okay, and the y one this is the y phase, front one, and bottom one is the z phase. Okay, so the left hand side is the x phase, right hand side is the x plus delta x phase. Okay, front one is the y phase, and the rear one is the y plus delta y phase, and bottom one is the z phase, and the top one is the z plus delta z phase. So we have 6 phases, and through all these 6 phases the heat can transfer, heat can flow. Okay, so we have to evaluate the amount of heat or the rate of heat which is transferred across these all 6 phases. Okay, so let us consider this is the amount of heat which is transferred through x phase, or to enter through x phase. So as I said, because we have to consider the area across which the heat is going to be transferred. So what would be the area of this x phase? So the area of x phase is delta y and delta z. So this is the cross sectional area through which the heat is going to be enter into the control volume, right? And this is the amount of heat which is which leaves from the x plus delta x phase. Okay, so this is q double prime x plus dx dy into dz. So this dy and dz is the cross sectional area which is available for the heat transfer. Okay, similarly for y phase, we have the information about the y phase, that is qi dx into dz, and this is the rate of energy in through y phase, and this is the rate of energy out through y plus delta dy phase, and this is the rate of energy which entered through z phase and leaves from the z plus dz phase. Okay, so we have to convert this physical situation into the mathematical form. So we have to use, so let's identify the amount of heat which enters through different phases and leaves through different phases. So as I said, this is the amount of heat which enters through x phase, that is qx double prime dy into dz, and this is the amount of heat which leaves through the x phase, that is q double prime x plus dx and dy dz. So we have to do some mathematical operations. So in this way we can identify how much amount of energy which is going to be transferred. So by using the Taylor series expansion, we can identify the amount of heat which leaves from the control volume. So we have to identify what is exactly the amount of heat which leaves from the control volume. So that is q double prime x plus dx is equal to q x double prime plus delta qx upon delta x times delta x. So plus delta square qx upon delta x plus dx square. So in this way we can have the Taylor series expansion. So by dropping the higher order terms, because higher order terms is not required for the evaluation of amount of heat which leaves from the control volume. So that's why we drop the higher order terms. So this is the we can identify the total amount of heat which leaves. So this is the net flow of heat in x direction, that is minus delta qx double prime upon delta x dx into dy into dz. So this is the total amount of heat which flow in x direction. Similarly, we can identify the in y and z direction as well, right? So we have all the terms, the rate of energy in and the rate of energy out from the control volume. Okay, so now we have to identify the amount of heat which is generated in the control volume. So or per unit volume. So this is the amount of heat. Let's consider the amount of heat, that is q dot, which is generated in the control volume, and the dimension of the control volume, that is dx, dy and dz. So collectively it gives the volume, so per unit volume. So this q dot dx into dy into dz, this is the rate of heat which is generated within the control volume, right? So we have almost all the information. Now only the left part is the rate of energy which is stored within the control volume. So as I said, the control volume has its own mass, whereas surface doesn't have their own mass. So because the control surface doesn't have their own mass, so they do not store the energy, but control volume can store the energy. So that's why, so the amount of energy which is stored within the control volume, so that this is the amount of energy which is stored within the control volume. So, or I can say the rate of change of energy within this control volume. So that is rho Cp delta T upon delta T, where delta T represent the change of temperature, whereas delta small t represent the change of time. So that is a change of temperature with respect to time. So, and per unit volume. So this is the rate of change of energy within the control volume. So we have all the information about the amount of energy which enters into the control volume and the amount of leaves from the control volume. Now we have to put all these mathematical form of the information, or the information in mathematical form, in this heat balance equation or the conservation equation. So by substituting all the quantity, all the information in this energy conservation equation, we have this mathematical form, and by solving simplifying all this mathematical form, we have this information. So by substituting the value of qx plus dx, qy plus dy, and qz plus dus from the conductive heat flow, we have the final form of the mathematical equation is this one. So minus delta qx upon delta x times dx minus delta qy upon delta y times dy minus delta qz upon delta z into dz plus, so this is the first three terms represent the net flow of heat in x, y and z directions, and the second so the fourth term represent the rate of energy generation per unit volume, and the right hand side term represent the rate of change of energy within the system or within the control volume. So since from the Fourier's law of heat conduction, we are familiar as of now, that is what is the rate of heat transfer per unit or what is the rate of heat flux. So that qx is equal to minus k dt upon dx qx is equal to minus ka. So where a is the cross sectional area, so for this case the area is dz into dy into dz, and dz into dx for the heat flow in y direction. Similarly for z direction, dx into dy is the area. So we have to substitute the value of qx, qy and qz over here. So after the substitution of this Fourier law of heat conduction, we have the final form of this equation. We have the final form of this equation, that is delta upon delta x bracket kx times delta t upon delta x, similarly for y and z as well, plus the rate of heat which is generated within the control volume and the amount of heat or the rate of change of energy within the control volume. So this equation is exclusively used for isotropic system, but let's consider we have an isotropic system for which the thermal conductivity does not vary with space or with spatial coordinates. So for kx is equal to ky is equal to kz. So for that case we can take the common, or we can have the k thermal conductivity which is constant for that particular case. So this equation is only used for the heat diffusion equation for n isotropic system. Okay, so but for isotropic system we will have the different form of this equation. So basically from this heat diffusion equation we can obtain the information about the point to point variation of heat within the medium, or net rate of heat transfer by conduction within the control volume, plus the rate at which the heat is going to be generated and the rate at which the energy is stored within the control volume. So as I said, the basic difference between the thermodynamics and the heat transfer. The thermodynamics inform us about the quantity of heat at initial stage and the final stage, or I can say the energy which is stored within the control volume, and it becomes a point function. But when two systems are in thermal equilibrium, or the system which goes under the process of thermal equilibrium, so for that case the heat is going to be transferred from high temperature point to the low temperature point. So that will that type of information we can obtain only from thermodynamics, and that becomes known as path function. Okay, so but in the case of heat transfer we can have the value of at which rate the heat is transferred in heat transfer, right? So as I said, for isotropic system we can consider the thermal conductivity, which is a transport property of the system, does not vary with spatial coordinates or x, y, z. So for that case the mathematical form of the heat diffusion equation will change, and the new form of the the heat diffusion equation is K delta square T upon delta x square plus delta square T upon delta y square, and delta square T upon delta z square, plus the rate which is heat generated and the energy stored within the control volume. Okay, and it is also known as delta. We can also write this heat equation in the delta operator form, where K is K del operator square T plus Q dot and is equal to rho Cp dt upon dt. Okay, so the final form of the heat conduction equation or heat conductive equation, this is the heat diffusion equation for constant thermal conductivity or for isotropic system, and this equation is also known as Fourier-Biot equation. Okay, we have done all these exercises, mathematical exercises, but what information we can obtain from this mathematical equation? So because ultimately our objective is to obtain what would be the expected temperature profile within the solid body or within the control volume. So if we know the point to point variation, because from this mathematical equation we can have the information what is the point to point variation within the control volume. So in order to simplify this equation or simplify this second order partial differential equation, we have to assume some important assumptions to simplify this mathematical equations. So for that we have to convert, or we have to consider some properties. So this rho Cp upon K, which is known as thermal diffusivity, where alpha is the thermal diffusivity. So thermal diffusivity of the system, which is a controlling transport property for the transient conduction. Okay, so means this thermal diffusivity which can control the temperature propagation within the system. Okay, and Q by K is a rate of energy generation per unit volume. Okay, so this alpha, which is a thermal diffusivity, which is equal to the heat conduction upon the heat storage. So as much as the heat can stored, the thermal diffusivity will decrease, and as much as the heat conduction will increase, the thermal diffusivity is also increasing, right? So the same and this alpha is also known as the transport property. As I said, this is the transport property that is known as thermal diffusivity. Similarly, in case of momentum transfer, we have the momentum diffusivity. So basically that tau is a momentum diffusivity or kinematic diffusivity, or in case of mass transfer we have the diffusivity. So this is the diffusivity, molecular diffusivity in case of mass transfer, but I will not go into that detail of momentum diffusivity and molecular diffusivity as of now. But the common thing is the unit, the SI unit for all these transport property will be same, that is meter square per second. Okay, so in order to simplify that heat diffusion equation or Fourier-Biot equation, we will assume some important assumptions, and by assuming that important assumption we can solve that second order partial differential equation. Okay, so we'll assume only one dimensional heat flow, means we'll have the heat will flow only in x direction. So no heat generation, so we'll drop that term, and also we also consider the system as a steady state, means once it achieve the equilibrium, the temperature will not change with respect to time. Okay, so if we utilize or if we apply all these three assumptions for this heat diffusion equation, so because it is one dimensional heat flow, so the temperature change in y direction and temperature change in z direction will cancel out, and the heat generation will also cancel out, because we consider the heat generation, there is no heat generation, and also the steady state, so we'll have the right hand side term will also get rid of. So the simplest form of this equation, that is d square t upon dx square is equal to 0. And because it is flowing only in one direction, that's why we are dropping that partial differential sign. We can only use d sign, or d square upon d square t upon dx square. So this is the temperature is a linear function of direction, we can say, but we have to prove that one. Okay. So this is the Fourier. So as I said, the Fourier-Biot equation may be reduced under the specific condition or by assuming various assumptions. So we assume steady state. So let's consider we have a case in which the heat is transferred in all directions and the heat is also generated, but the system as it steady state. So if the system is at steady state, so that this type of equation is known as Poisson equation. That's right. And the diffusion equation, in this case, the heat generation is not considered. So we'll have only the heat is transfer in all possible direction, and the heat is also stored within the control volume, but no heat generation. This is known as diffusion equation. And the last one is known as steady for Laplace equation. In that Laplace equation, we consider no heat generation and no heat is storage. Okay. So for so this is in this way we can have the different form of heat Fourier-Biot heat diffusion equation. Okay. Now let's so as we consider the simplest possible geometry, that is Cartesian coordinate. So similarly, we have the different coordinate system, like cylindrical coordinate system, spherical coordinate system. So we'll will not go into that detail, but we'll go for the what is the mathematical form of that equation, that is heat diffusion equation in case of cylindrical coordinates. So the heat, the temperature, as I said, the temperature is the function of radial direction, temperature is the function of phi, temperature is the function of z, and it is also a function of time as well. So the final form of this equation for the cylindrical coordinate, so this is the final form of this equation for cylindrical coordinate. Similarly, for spherical coordinate, we have this mathematical form of the heat diffusion equation, but will not go into that detail as well, because the concept is same, but only the mathematical approach will be different, mathematical form will be different, or the appearance of that equation will be different, but the approach is same. We have to consider the energy which is coming through x phase or through a particular phase and leaves from a particular phase. Similarly, from other phase and leaves from other phase, energy which is generated, which is and energy which is stored within the control volume. We consider all this. The concept is same. Only the mathematical approach is only different. Mathematical form is different, right? So we'll obtain this equation. So after gaining this all this information, after solving this all. Obtaining this mathematical equation, what is objective? Our objective is to exactly identify the how we can proceed to solve this equation. So in order to solve this second order partial differential equation, we'll have some constraints. So we have some boundary condition. So now what are those boundary condition? We have to discuss in very brief. So the boundary condition is there are various boundary conditions. So we have first boundary condition. Let's the surface temperature is provided. That is Dirichlet condition. So for that case, the temperature is Ts because temperature is provided. Second boundary condition is constant surface heat flux. Means the heat which is flowing across the control or through or towards the control volume, the heat is constantly flow. Means the heat flux is flow constant. Third boundary condition is adiabatic or insulated wall. So for that, the heat is not transferred across the the insulated wall. And the fourth boundary condition is the convection surface condition, or the mixed boundary condition. So at this mixed boundary condition, as we discussed surface energy balance part, we consider the amount of heat which is transferred exactly at the interface of solid object and the ambient, means the heat which is conductive heat transfer will be equal to the convective heat transfer. So we'll use all these boundary condition in order to solve the differential equation, right? So let us consider we have a plane wall. We have a plane wall in and across this the heat is going to be transferred. So this is the direction of heat which is transferred. So at one surface the temperature is maintained at T1, and at another surface temperature is maintained at T2. So of course in this case the temperature T1 which is maintained at first surface is greater than the temperature which is maintained at second surface. So T1 is greater than T2. So the heat is transferred from T1 to T2, right? So we have to evaluate the quantity of heat, of course, and the rate at which it has to be transferred because of temperature difference or by virtue of temperature difference. So as we are going to discuss about only the one-dimensional heat conduction steady state. So if it is a one-dimensional steady state, so we have to get rid of temperature variation in y direction, in z direction, and also the steady state part, that is 1 upon alpha delta t upon delta t. And also one more assumptions we have to make, that is heat generation is there is no heat generation. So simply the temperature is a function of x, not a function of time. So we have Laplace equation, that is d square t upon dx square is equal to 0. So after integrating this equation, we'll have the equation that is which is accompanied with integration constant. So we have to solve this integration. So we have to obtain the value of integration constant, that is C1 and C2. So so first boundary condition, that is at x equal to 0, the temperature is T1. At x equal to at x equal to L, that is the maximum length of that control volume. So at x equal to L, the temperature is T2. So we have to substitute the value of x and obtain the value of C1 and C2, and after obtaining the value of C1 and C2, we have to resubstitute in that equation, and after the substitution of C1 and C2, we'll get the temperature profile which is linear. So this is so in this way we have to obtain the temperature is a linear function of x, x, or temperature is a function of x, but it varies in linear form. Okay. So by using Fourier law of heat conduction, we can also relate the cause or the potential. Okay. So for heat transfer, as I said, the temperature difference is the potential. Okay. And because of the temperature difference, the heat is flowing. So the heat which is flowing, which is considered as a cause, and the potential because of the cause takes place, that is known as temperature difference. Okay, and the rest of the things will be considered as, and the quantity which restrict to flow the heat from high temperature to low temperature, that is known as resistance. So from Fourier law of heat conduction, that is Qx is equal to Ka upon L. L is the thickness of the slab, T1 minus T2. So Qx is equal to, so this L by Ka becomes the resistance for heat transfer, whereas T1 minus T2 becomes the cause through which heat is transferred, and Qx, the potential, and Qx is the cause for heat transfer. Okay. So this is known as the conductive resistance, which is L by Ka, and And similarly, you can also identify the convective resistance as well. But convective heat transfer we will not cover in this lecture. So we'll only restrict to conductive heat transfer. So so in this way, you can identify what would be the temperature profile within the control volume, and for one dimensional heat flow, most of the cases will get the linear profile. So we'll start from the basics of the thermodynamics, and we in today's lecture we discuss about the what is the basic of heat transfer, what is the relevance of heat transfer, what is the application of subject in various day-to-day life, and its mathematical form, which is also known as the foundation of convective heat transfer. So that's all from today's lecture, and if you have any doubt or any query, you can just ask me. Thank you.